right, part B of this question reads, the sun has a surface temperature of 5,800 Kelvin. The wavelength lambda sub max of light for which the maximum rate of emission occurs from the sun is 500 nanometers. Kind of in the green, interestingly enough. I guess yellow-green. The scientist observing the star in A finds that the wavelength for which the maximum rate of emission occurs from the star is 430 nanometers. Show that the surface temperature of the star in A is approximately 6,700 Kelvin. Explain your reasoning. And so this is the Wien displacement law. I spell it, but it's pronounced Wien. And he said that the wavelength max is proportional to 1 over the temperature. Okay, so that's sort of the reasoning that we need to do this, to set up this proportion. And so let's see, we want to kind of solve for this because we're sort of showing that the temperature of the distant star is this. And so let's kind of make like temperature is proportional to 1 over that then. And so let's make the temperature of the distant star sort of like the numerator. So we'll kind of solve for that. So we'll set it up like this. The temperature of the distant star, the thing we're solving for, over the temperature of the sun, right? So we're sort of using the sun to compare this. So the temperature that we want to know over the sun is going to be equal to now. So since we're using a proportion, we just sort of set up, okay, the ratio of these temperatures are going to be equal to sort of like the inverse ratio of the maximum wavelengths. And so what goes with the sun goes up here, right? And what goes with the distant star goes down here because they're inversely related. So the sun had the peak wavelength 500, and we can keep the units, you know, nanometers because they're just going to cancel out, right? That's the beauty of a proportion. And we're comparing that to 430 nanometers, which is the peak wavelength for the star. So remember, here on Earth, we can take spectra, we can measure what the peak wavelength is. We can thank, you know, the giants upon whose shoulders we stand to, you know, reason our way and say, okay, now we know what the temperature of this distant star is. And so the working would be 500 divided by 430 gives you sort of the ratio of the wavelengths on this side, 1.16. If we multiply both sides by 5,800 times times 5,800 over here, then I've solved that the temperature is 1.16 times 5,800 equals 6,744. That's the calculator value, which is indeed about 6,700, right? If you round it to 2 significant digits, which we got there. Right. So indeed, we've shown that that temperature is approximately that. So that's how those calculations go.